Welcome to this session. In this session, we are going to discuss about adjoint of a square matrix. So the adjoint of a square matrix is simply the transpose of the determinant of the matrix of cofactors. So definition. The adjoint of a square matrix A is a transpose of the matrix of cofactors of A. So that's how we define the adjoint of a square matrix. Now, property of adjoint. I remember, so adjoint is denoted by add A. So to mean adjoint of A. So this is how we denote it. So property of adjoint matrix so the product of a square matrix A by its adjoint is equal to an identity matrix multiplied by the determinant of the matrix A, i.e. adjoint of A multiplied by the matrix A is the same as the determinant of A multiplied by an identity matrix. So let's prove. So proof. So let A, let's just consider A to be a 3 by 3 matrix. So we have A11, A12, A13, A21, A22, A23, A31, A32, A3 with the square matrix. Then let matrix C be given by C11, C12, C13, C21, C22, C23, C31, C32, and C33 be the matrix of cofactors of A. Then, by definition, adjoint of A is the same as C transpose, which is the same as C11, C12, C13, C21, C22, C23, C31, C32, C33. So that's by definition. Now, adjoint A times adjoint of A is the same as A11, A12, A13, A21, A22, A23, A31, A32, A33. You multiply this one by adjoint is C11, C12, C13, C21, C22, C23, C31, C32, C33. So this is the definition of this product. And so we'll have multiplication of this 3 by 3 matrices. So we'll have row column. So you have A11, C11 plus A12, C12 plus A13 times C13. And then element here will be A21, C11 plus A22, C21, C12. Number is row column. So plus A22, C12 plus A23, C13. Then here we'll have A31, C11 plus A32, C12 plus A33, C13. And then here we have this row, this column. So we have A11, C21 plus A12, C22 plus A13, C23. And then here we'll have A11, C31 plus A12, C32 plus A13, and then C33. And then here we have this row, this column. We'll have A21, C21 plus A22, C22 plus A23, C23. And then here we'll have this row, this column, A21, C31, plus A22, C32, plus A23, C33. And then here we'll have this row, this column. So A31, C21, A32, C22, A33, C23, and then this row, this column, A31, C31, A32, C32, and A33, C33. And you see in this product, you should see that this sum, and this sum defines determinant of A, because remember, determinant by cofactor method is simply if you take any row, you multiply the elements by their corresponding cofactors, then you get the determinant. So A11, A11, A12, A13 is the first row of this matrix. So if you take elements along a row, multiply each element by its corresponding cofactor, and then you sum them, you define the determinant. Similarly, A21, A22, A23, this element in this second row, if you multiply by their corresponding cofactors, you get determinant of the matrix. A31, A32, A33, elements along this row, multiplied by the corresponding cofactors, defines the determinant. So therefore, this is the same as determinant of A, and then this is the same as determinant of A. This is the same as determinant of A. So the only work is for us to show that all these other elements of main diagonal elements, their values are 0. So I'll pick, for instance, let me pick this element here, A31, C11, plus A32, C12, plus A33, C13. Now, remember, this is the matrix A11, A12, A13, A21, A22, A23, A31, A32, A33. So this is our A matrix. I remember, if you want to find their cofactors, you simply multiply the minor of every element by its corresponding sign given by -1 raised to power r plus c, where r is the number of rows, c is the number of columns. But it can always be shown that the sign of this element will be plus, the sign of this is minus, the sign of this is plus, minus, plus, minus, plus, minus, plus. So signs alternate. The first one plus, and then alternate negative, plus, etc. So C11 means the cofactor of this element in position 1, 1. So C11, so say you have 3, 1 into, so C11, you delete this row, this element, delete this column. So remain with this submatrix, and then you define its determinant. So we have A22 times A33, A22 times A33, minus A23 times A32. So that is the cofactor of C1, 1. And then 1, 2. 1, 2 is this element here. So is cofactor. So the sign here is negative. So I'll have negative A3, 2. And then 1, 2, this one here. So deleting this column and this row. So I'll have A21 times 3A33. And then once you have deleted this and this one here, so I have A23, A31. And then 1, 3. 1, 3 is this position, so the sign is plus. So I'll have plus, and then A33 into. So delete this column, delete this row. Then we'll have this deleted, you have this submatrix. So we have A21, A32 minus A22, A31. So we'll have multiplying here, A31, A22, A33 minus A31, A23, A32 minus A32, A21, A33 minus will be plus A32, A23, A31, and then plus A33, A21, A32, and then minus A33, A22, A31. Now you see in this product, A31, A22, A33, and we have minus A33, A22, A31. So this and this one cancels out because they're the same terms with opposite signs. And here we have A31, A23, A32. You see, we have another one here, A32, A23, and A31. So this and this cancels out because they're the same terms with opposite signs. And A3 minus A32, A21, A33, A33, A21, A32. This also and this one cancels out. So this will give you 0. So therefore, this element here, if you expand it, you get 0. And as an exercise, also show that A22, C11, A22, C12, A23, C13. If you expand this, will also get 0. Similarly, this will give you 0. Similarly, this will give you 0. This will give you 0. This will give you 0. So therefore, and these elements along the main diagonal forms the determinant of A. So we'll have, this implies that the product of A and adjoint of A is the same as the matrix formed by, this is the determinant of A, this is 0, this is 0, 0, determinant of A, 0, 0, 0, determinant of A. Now, because determinant of A is a common factor or a common number inside this matrix, we can factor it out. We say determinant of A multiplied by 1, 0, 0, 0, 1, 0, 0, 0, 1. So remember, these are matrix, not a determinant. So don't get confused by what we are doing here and when you are calculating the determinant. So they are different things. So this is what we have. And clearly, you can see that this is an identity matrix. So this is A determinant, times an identity matrix, and we had A times the adjoint of A, and this is what we were to prove. So therefore, this is the relationship between the matrix and its adjoint. And let's see how inverse of a matrix can be obtained using adjoint matrix. So we say, from what we have proved, we know that A times adjoint of A is the same as the determinant times an identity matrix. So dividing through by the determinant, because just a number, so determinant of A times 1 over determinant of A, we get A times 1 over determinant of A adjoint of A is equals to an identity matrix. Now, pre-multiplying both sides by A inverse, we have, so I multiply by A inverse, so A times 1 over the determinant of A adjoint of A equals to A inverse times the identity matrix. And you see A inverse times A is an identity matrix. So multiply by 1 over determinant times adjoint of A equals to, now A inverse times identity matrix is just A inverse. So this implies that A inverse alone. Now remember, the identity matrix here and the adjoint here have the same order, so multiplication is possible. And identity times any matrix of the same order, you get the same matrix. So this is the same as just saying 1 over determinant of A times the adjoint of A. So this is how we calculate determinant, not determinant, the inverse of a matrix by adjoint method. So just find the determinant, then find the adjoint, and simply take the adjoint times the reciprocal of the determinant. And key thing for you to note is that A inverse exists if and only if the determinant is non-zero. Because we are dividing through by determinant, so determinant must always be non-zero for you to be able to find inverse of a square matrix. So if the determinant is 0, then that matrix is referred to as singular, and it's not, we can't define its inverse. So the inverse will only be defined whenever the determinant is non-zero. Thank you.